Hi guys, I'm Hao and today I'm going to walk you through an interesting volume problem. So the region R is the area between the coordinate axes, which are the x and the y axis, and this function y equals 2 to the x and the line x equals 2. And R is also the base of a solid form when semicircles are drawn perpendicular to the y-axis. So we're going to set up a volume expression to find the volume of this solid. And what I'm going to do now is I already sketched the graph of these lines and this function, and this is the line x equals 2, the green line. This is the red line is going to be y equals 2 to the x. So the region R is essentially this R over here. The inside part of these things are bounded by all of these lines, and we're gonna find the volume of when semicircles are drawn perpendicular to the y-axis inside this region. So now to visualize these kind of semicircles, I'm gonna draw it on this two-dimensional sketch. And because the semicircles are perpendicular to the y-axis, so we are slicing this graph horizontally, and you can imagine that I'm going to draw lines like this, like line segments, I think. And these things over here represent the diameters of infinitely many semicircles. And okay, so these lines I already draw it when y equals 1/2, 1, 1.5, and 2, and go on. And in the two-dimensional graph, as you can see, these just looks like kind of line segments. So we really want to find out how these line segments are actually semicircles in the three-dimensional. So now I'm going to switch to the Desmos three-dimensional calculator to see what is actually going on. Okay, now we already moved to the Desmos three-dimensional graphing calculator, and as you can see, I already sketched the line x equals 2 and the curve y equals 2 to the x. And here are some line segments that I already did last time in OneNote, as you can see. You can imagine it like the semicircles actually in the two-dimensional shape. But what if we're gonna add one more dimension, which is the z dimension, and we're gonna see its semicircular shape of this weird thing over here. And I already have sketched all of these semicircles. So what we're gonna do is that we're gonna calculate the area of every single slice of the semicircular shape, and then we're gonna multiply it by its thickness over here. How thick is it? It's gonna be dy, and then we're gonna add them up, or in the calculus means we're gonna iterate it from the bottom to the top, and it looks really complex, but it's just stacking up shapes, and that is the geometry of iteration. So what we're gonna do is that we're gonna calculate the area of every single slice of the semicircular shape, and then we're gonna multiply it by its thickness over here. How thick is it? It's gonna be dy, and then we're gonna add them up, or in the calculus means we're gonna iterate it from the bottom to the top, and it looks really complex, but it's just stacking up shapes, and that is the geometry of iteration. So we need to sum up the volumes of these really thin slices, and each slice is a semicircle with a small thickness. So I'm going to write like this to visualize it, and its thickness right over here, like this. Okay, so we have the basic radius over here, and this is the thickness. And because the thickness is vertical along the y-axis. As you can see over here, this is the thickness. These are the thickness. And they are really, really small along vertically the y-axis. So I'm going to call it dy over here. And the next thing we're going to do is, if we want to find the volume of these really thin slices of a semicircle, we're going to also find the area, the surface area of this one over here. And because the area of a circle is pi r squared, right? But this is just semicircle, half of a circle, so we're going to multiply it by 1/2. And because to make the math easier, I'm going to use the diameter, because we're just going to take the right x minus the left x value. And what I'm going to do is I'm going to replace this by d, which is diameter, 1/2 of pi times diameter over 2 square, which is simplified into pi over 8 of d square. So the volume of this really thin slice is going to be pi, I'm going to call it dv equals a in terms of y times dy. This is the area. Okay, so because I'm going to solve it in terms of y, because I already did the thickness thing equals dy over here, so I'm going to make this area function in terms of y also to make the math easier. So our volume element is pi over 8 d squared times dy, right? So now we just need to find the diameter over here. I will make another color. We're just gonna figure out the diameter over here, which is kind of complex in this situation. And I'm gonna divide it by this simple math. Diameter equals x right minus x left. So in this particular shape over here, we see in the region R, we have two different diameters. So the first region from 0 to 1 over here, the radius, the diameter is always the same, which is 2. So I'm going to write here from 0 to 1, 0 less than or equals y less than or equal 1, t equals 2, and on the interval from 1 to 4, y equals 1 to y equals 4, we see the radius dramatically changing over here. This part over here. So x right is still 2, right? Because it's bounded by x equals 2, so x right equals 2 always. So I'm going to write here 2 minus. So now we're going to figure out the x left over here. And if we're just going to call it x, because it's basically the distance from horizontally from the origin to that point, for example, like this. We normally call it x for easier math, but in this case, because we are iterating using the variable y, because I already used dy over here, so I'm going to make x into something in terms of y, because we already have this function y equals 2 to the x. So if we rewrite it, x equals logarithm 2 of y. So I'm going to plug it in here. So now we're going to combine them for the total volume expression, and the ultimate volume equals the volume from the first region over here, which is the integral from 0 to 1 of pi over 8 times 2 squared dy plus the integral from 1 to 4 of pi over 8 times 2 minus log 2 of y square dy. So I already did this type of iteration by my hand without the calculator. You can pause the video to see the process because it's so long, so I didn't put it in my video. So I just scrolling down to let you easier to see it. So after all of this, I got this solution, this answer for the whole problem, and the total volume is gonna be 3 pi over 4 ln of 2 squared minus pi over 2 ln of 2, which is 2.638. But when I checked with my calculator, I also got 2.638. So they are both the same. So we just finished it. Thank you guys for watching me.